those who are not here can review this. Okay, so as I promised, I wanted to do a dive into what you're learning for week 2, and what I really wanted to go into is why we do the things we do and why you're learning all of these properties and how they're used, and why that, just when we're solving equations, why everything works. Because if you understand that, then you might have a better understanding as we move forward, because you'll see how all of these things are connected. So this is my hope, that it's going to start making connections. So we start off this week in section 1.7. We learn about the properties of real numbers. And so these are the commutative property, the associative property, distributive property. We've got the identity and the inverses, and we have all these rules. And why do we have these rules? Well, if we don't have any rules about math, then people are going to be just doing the math any way they want, and there's going to be no consistency. We're not going to get the right answer. It reminds me, I don't know if you've seen on the internet, they often have these math problems, and it's like, can you solve this problem? What's the correct answer? And people get multiple answers, and it's because people don't remember the rules, and so they're not following the right rules, and then people are getting different answers. So we have these rules for a reason, so that we have one answer every time you see a problem, so that everybody looks at it and knows exactly what to do. And the way that math works is that we basically start with these basic rules, and then we use those rules to create new rules, and everything kind of grows. And so the most basic rules that we have are these properties of real numbers, and then we also have the properties of equality. And these are what the rest of algebra is basically built off of. You start with these rules, and then you combine them, and you make new rules. And this is what mathematics is all about. People that are getting PhDs in math are basically coming up with new rules, which we call theorems, just based off of existing things. Like, basically, they're just putting things together and seeing what happens, and if it's interesting. And if it's interesting enough, we turn it into a rule. So that's what math is, and what we're doing with the algebra and the most basic rules here are just seeing where everything started, basically. And so we're just starting with the basics, and then hopefully, as we go through the class and we start getting into more complicated equations, you'll see how everything comes back to these same rules, and that everything boils down to the same things over and over again. We're just adding more steps to it, but that at the end of the day, you always end up doing the same things, such as solving for x, adding and subtracting things to both sides of an equation. They all get back to the same basic things. It's like you're making a recipe and you have lots of different recipes, but they maybe all, have the same base, like rice, or, you have pasta dishes. So that's sort of what these properties are. They're the base that you're working with. So the first property that I want to talk about is commutative property. And when I learn, I like to understand the terminology and kind of figure out where do these words come from, because if you understand what the words come from, then that can give you an understanding of what it means. So commutative can come from the word commute. So I looked up commute and looked up the where it comes from with the Oxford Dictionary, and it actually comes from Latin. You can see this picture here. The word commute comes from Latin, and the two pieces of the words that mean to change altogether. And so that was in place with the Latin word, and then with how it was used in English, basically means you're interchanging two things. And that's what the commutative property is that you're flipping, you change the order. You can change the order of addition, you can change the order of multiplication. And you can do this because you get the same answer. If you think about it, and I have some examples here, you know that 2 plus 5 is 7, and if you did 5 plus 2, you're still going to get 7. It's going to be the same thing. The order that you add those doesn't matter. And it's the same thing with multiplication. 2 times 5 is 10. 5 times 2 is 10. Everybody knows these, but they don't realize that there's actually a mathematical rule that tells us why this is. And this is just one of the rules that we use when we start solving to make things easier for us. And it's not, we didn't just make up the word commutative, like it actually comes from a word that kind of makes sense once you know what it means. You're interchanging things, you're rearranging them. Now, we only ever talk about the commutative property with addition and multiplication. And most of these rules, we're always looking at them in terms of addition and multiplication and not with subtraction or division. And there's a reason for that. So if we were looking at, say, subtraction, and 2 minus 5 gives you -3, but that's not the same thing as 5 minus 2. 5 minus 2 is a +3. So subtraction, the order, you can't flip the order for subtraction. It actually matters. Addition, it didn't matter, but it does matter with subtraction. So that's why we don't have a commutative property with subtraction. However, if you really want to dive into it, I said that these rules are the basis for everything that we do. We can use these rules to figure out things. We can actually work with the rules that we have, figure out, well, if I did want to make a rule for 2 minus 5, or if I wanted to make a rule for subtraction, what would I do? So I'm going to briefly move my keyboard out of the way so that I can write with my stylus. So I'm going to just show you what we can do with our rules, what we know, and to kind of show you, this gives you an idea of what mathematicians do, like those people with those PhDs, what are they doing all day? You'll get an idea, and you'll see how we use our thinking and we take what we know to figure out what we don't know. So let's start. We want to know, okay, we know that 2 minus 5 is not the same as 5 minus 2, because one side is -3, the other side is +3. So those are not the same thing. But so we want to know, okay, what would it be the same as? You know, if I took that 2 minus 5. So I start with 2 minus 5. And the one thing you think about, what do I know? Well, I know that subtraction is the same as adding a negative. That's one of the basic things you learn about subtraction. So 2 minus 5 is the same as 2 plus a -5. And this is actually, this comes from the definition of subtraction. So subtraction is actually defined as adding a negative. So you can turn any subtraction into adding a negative, and I recommend doing that when you're learning algebra because it makes it easier to see the rules that we're applying. So I'm like, okay, so now I've done the first thing. I took something that I know and I rewrote my subtraction, adding a negative. So let's keep going with this thought. Well, now I have 2 plus -5. What else do I know? I know the commutative property of addition. That commutative property of addition says you can rearrange the order. So this is the same as -5 plus 2. So I'm going to write this down. And this is the commutative property. And I usually don't write addition there, I just write commutative property. So I'm just using what we know. And now this has given us something new, because now we can take our 2 minus 5, and now we've determined that it's the same thing as -5 plus 2. If I'm following step by step, I went to here and then to there. You can kind of follow the logic there, what I set it equal to. So we know that 2 minus 5 is the same thing as a -5 plus 2. So what we did is we've, in a way, sort of come up with a new rule, but we've used our existing rules of what we know in order to rewrite this in a way that makes more sense. So, and I say it makes more sense because a lot of people look at a subtraction like 2 minus 5 and they may struggle with figuring out what that is in their head. But if you use these properties and you look at it as -5 plus 2, understanding that -5 is in debt and now you're adding 2 more, like let's say you're in debt $5, you just paid off $2, so now you're in debt $3. Like, it makes more sense looking at it as a -5 plus 2 than it does necessarily from a 2 minus 5. So this is why we have these rules. We have these rules because they often can make things easier to understand or put it in a different way where you're like, okay, I see what this is saying. You know, if you struggle with it with one way, try to use your rules to see, oh, this is a different way to look at it. And this is the thing that all about math. And actually what I try to tell people is, if one way doesn't work for you, try a different way. This is why I teach multiple ways to do a problem, because sometimes you just have to use some rules and to put it in a form that makes sense to you. So that's how we could use the commutative property with subtraction, even though there is no technical commutative property with subtraction. So let's do the same thing with division. So we have the commutative property of multiplication, where the order of multiplication doesn't matter, but with division, the order does matter. If I did 2 divided by 5 in my calculator, I get 0.4. And if I did 5 divided by 2 on my calculator, I get 2.5. So those are not the same thing. So you can't change the order of division. But let's say I had 2 divided by 5 and I didn't know what to do with it, and I wanted to say, okay, well, what is there a way I can rewrite that in a way that makes sense? And so we're going to do the same thing that we did with the subtraction. So I'm going to start with 2 divided by 5. So division is actually the same thing as multiplying by the reciprocal. So division is also defined in terms of multiplication. So this goes back to with fractions. Whenever you divide, you have a fraction, you divide by a fraction, you multiply by the reciprocal. It's the same thing even with whole numbers. So if I'm dividing by 5, that's the same as multiplying by 1 over 5. And this is actually the definition of division that we just used. So division is defined in terms of multiplication. And so any division problem you can rewrite in terms of multiplication. It usually ends up having a fraction, but that's totally okay. So now we have this 2 times 1/5. Okay. Maybe we can use our commutative property. We can rearrange that and say it's 1/5 times 2. So if you think about it, you might say, okay, 2 times 1/5. I don't know how to multiply something by 1/5. But if I have 1/5 of something and I multiplied it by 2, I know I doubled it. So that gives me 2/5. You see how that rearranging the order actually puts it in a way that makes more sense? So it's you know, it means the same thing, but you think about it differently, and you're like, oh, I know how to multiply by 2, versus then trying to think to multiply by 1/5. And so we now have basically determined that if you have 2 divided by 5, you can also think about that as 1/5 times 2. Which is basically just saying I have 1/5 and then another 1/5, so I'm going to get 2/5 out. So that is, once again, we use the commutative property to rearrange that in a way that makes more sense for the way that we think about numbers. It's easier to multiply by 2 versus trying to multiply by 1/5. So that's why we have the commutative property, and that's why it can come in handy. You can use it to try to think about things in a different way and see if that makes more sense. So the next property that we have are the associative properties. So we have 2 associative properties. We have one for addition and one for multiplication, just like commutative. So again, this comes from the word associate, and so I looked it up. Most of these words come from Latin, because actually You may have possibly noticed this when you're doing your research for the discussion this week, that a lot of our symbols, like the plus sign, came from the Latin word for and, et. They used to do math basically in Latin. Everybody wrote Latin. So this comes from Latin. You're combining two words together, add socius, to share, and eventually came to mean join. And so associate can mean join with a common purpose. And when we say things are joined together, we're meaning by parentheses. So we're using the parentheses to join these things together. And so that's where the associative property comes from. And so essentially it means that we can group things together differently and get the same answer. So I have still my examples of the 2 plus 5, and I added in plus 7. If you did 2 plus 5 first, that gives you 7, and then that plus 7 is 14. But you can also do it the other way. You can do 5 plus 7, which is 12, and then have 2 plus 12 and get 14. One is easier to do in your head than the other. The 2 plus 5 is easier to do first than 5 plus 7. So the associative property can help you do math in your head easier depending on the order that you add those things together. And it's the same thing with multiplication. You can group your multiplication as long as they're on a row. You can do the multiplication in different orders. So I could do 2 times 5, which is 10, and then times 7, which is 70. That's pretty easy to do in my head. Or you could have 2 times and then do 5 times 7. So you do according to the order of operations, parentheses are first. So we do 5 times 7 first, which is 35, and then do 2 times 35, which is also 70, but harder to do in your head. That's not something that usually you know, but doing it the first way is a lot easier. So these properties, you can use them to your advantage to find answers quicker and to do mental math quicker by understanding these rules. But once again, we don't have rules for subtraction or division. We can make it work with subtraction, but you have to do some finagling. So I'm going to just kind of demonstrate that like I did with the commutative property. So I can't just rearrange the order of subtraction here. And let me do the subtraction so you can see that. So 2 minus 5, that's a -3. So -3 minus 7, that's -10. Now, on the other hand, if I rearrange my parentheses, 5 minus 7 is -2. You would have 2 minus -2, which is 2 plus 2, and you get a 4. These are not the same thing. So you can't just, if you have a series of things that are subtracted, you can't just subtract them in any order that you want, because you're not going to get the same answer. But if you understand how these rules work, you can rewrite it in a way that will allow you to do it in a different order. So again, I'm going to start with the left side. We have 2 minus 5 minus 7. First thing I always do is to rewrite subtraction as adding a negative, because that's where you can really see that where these rules hold. So instead of 2 minus 5, that's 2 plus a -5. And then instead of minus 7, that's the same as adding a -7. And again, we are allowed to do that because that is the definition of subtraction, is that adding a negative is the same as subtracting, and you can go the other way. Subtracting is the same as adding a negative. It allows you to go either way. So now that I've written it in terms of addition, I can use that associative property of addition to rearrange my parentheses. So I'm going to take the right side and first rewrite it so you can see what we're doing here. If I rearrange the parentheses, that means I'm now putting them around the -5 and the -7. So you can see if I wanted to do 2 minus 5 and then minus 7, if I wanted to do it in a different order, I would have to do -5 minus 7 and then add 2. You can't do 5 minus 7. It would have to be a minus 5 minus 7 because of the way that these properties work. So if you wanted to, you can even rearrange, turn this back. Let's see, the negative 5 stays the same, but that plus a negative 7 I could turn into subtraction. So really, let me actually rewrite this. If we have 2 minus 5, then minus 7, what this is really equal to is, if I wanted to do it in a different order, it would be 2 plus a negative 5 minus 7. So that minus sign has to go with the number, basically, is what we're learning here. You following the rules in the associative property of subtraction, that tells us if we had tried to do this on the right, we get the wrong answer, and that's because of where we put that negative sign. So I'm just following the rules that we have to figure out what's another way to do the problem. And so here I use the associative property. Now, you guys are not asked to do things like this, but I think it's important to understand why we do the things we do and to understand how these rules work and what you can do with them, because it kind of gets you into a thinking. It's a problem solving. Well, I have this. What could I do with it? How could I rewrite this? Okay, where does that take me? And that's the sort of thinking that you want to do when you're solving problems, especially when you get into word problems. You have to take what you know and just start messing around with it to see where you go from there. And that's how you really get good at word problems, is by just trying things out, seeing what works, what doesn't work. Does this make sense? Does it not make sense? That sort of thing. So let's do the same thing with the division. Just this is good practice so you can see how the rules work and you can understand what all of these symbols mean and all that. So if we have division here, so I've got an example, and it's going to come out in the decimals if you put it in your calculator. You got 2 divided by 5 first, following the order of operations, and then divided by 7. So this gives me a nasty number. I'm going to just write a few numbers, but it just goes on forever. But if I did the one on the right, and you put it in your calculator with all of your parentheses, and you have to do the inside the parentheses first, that actually gives you a totally different number. You get 2.8. So again, the order here of division, you can't just rearrange which division you do first because you get different answers. So parentheses really matter. That's one of the lessons here, is that where the parentheses are makes a difference in what your answer is. So let's say we have this 2 divided by 5 divided by 7 thing. And I'm trying to find a different way to do this problem. So just like with the commutative property of division, let's turn all of our division into multiplying by the reciprocal so that we can have the multiplication here. So we've got 2 times 1/5. The reciprocal of 5 is 1/5. And then also we have a division by 7, so that's reciprocal is 1/7. So this is just the definition of division, that we are allowed to do this. So this may not be handy in any way, but let's just keep going with the rules just to see what we can do. Well, if I have 2 times 1/5 and then times 1/7, I can use my associative property to instead do 2 times 1/5 times 1/7. And if you look at it that way, If we're trying to do a math problem and you're trying to do a problem with fractions, a lot of people are bad at fractions. But if you look at something like this, it might be easier for you to multiply those two fractions together than it is to multiply a whole number by a fraction and then to multiply by another fraction. Because we kind of know what to do when we see two fractions multiply together. You multiply across on the top and the bottom and on the bottom. So it's a little easier to look at something that's 2 times 1/5 times 1/7 and going from there. So that's one way that you can use this associative property, rearrange things, and get in something that might make a little more sense to you on where you're going from there. So this, again, we use the associative property. And if I wanted to, I can convert things back to fraction or back to the division symbol. But my point is that sometimes using these rules puts it in a way that's a little bit easier for you to work with. So why do we have these properties? Because it's easier sometimes to simplify if we rewrite the problem differently. Sometimes it's really, might look really complicated, but if you start using these rules, you can put it in a simpler form. So back to the history, because we were talking about this week in the discussion, the history of these symbols. The commutative property was actually used way back by the Egyptians and the BC, like, way back when they were building pyramids and all that. And they used it to simplify multiplication to make it easier. And then Euclid, who was a Greek mathematician, philosopher, he used the commutative property. He wrote a book of proofs called Elements. Of course, it was whatever the Greek word for elements is. But he basically wrote a book where he just had rules and then just said, well, where do these rules take me? And he's the father of geometry and saying, okay, you start with these rules. What is a line? What is a point? Where can I go from there? So he used the commutative property in that book. But the actual words that we use, commutative and associative, those didn't come by until the 1800s. Two separate guys came up with these terms. So Francois Servois, I don't speak French, but he was the first one to use the word commutative. And W.R. Hamilton, he was an Irish guy. He first used the term associative. So the actual words that we use today came around in the 1800s, but the concepts have been used for many, 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 many years. So just some other properties to note that are covered that you should know is we have the identity properties, which is basically if you add 0 to a number, it remains unchanged, or it's identical. That's where the word identity comes from. Or if you multiply a number by 1 or 1 by a number, you get the number out. So it doesn't change it. It's still identical to what it was. And we have inverse properties, where if you take a number and its inverse, and the inverse is basically the opposite of the sign for addition. So if you add a number and the negative version of the number, they cancel out. 2 plus -2 is 0. Those cancel out because they're on either sides of the number line, and so the middle part is basically 0. And then we have an inverse property with multiplication, where if you're multiplying a number by its reciprocal, those cancel out and you get 1, because it's basically you're saying 2 divided by 2 because the reciprocal is dividing. So those are the inverse properties. And then we've got the distributive property, which is used all the time. And this I always use arrows with. You're basically multiplying through the parentheses. So whatever's on the outside gets multiplied by the inside. So you'd have A times B. Oops, that's supposed to be B. That's a typo. And then you have A times C, and you can add those together. And you can go the other direction. So even if it's in the back, you can still do A times B and then A times C. So that's the distributive property. And if we wanted to go into a subtraction or things with division, that sort of thing, we can. We would use the same tricks that we did before, but I'm not going to work that out. I just wanted to give you an idea of, the kinds of things you can do with math, how you just follow the rules and see what happens. So that's basically 1.7, and then once we get into chapter 2, you start learning about the properties of equality and what we actually use to solve. And we have rules for equality just for the same reason that we have the rules for real numbers. We need to have some rules so that we know what to do when we're solving an equation. We need to make sure that everybody is solving it the same way and do it in the same order. Everybody gets the same answer. So we've got addition and subtraction properties of equality. So basically what these mean is that you can add a number to both sides of an equation, or you can subtract from an equation the same thing. So above here is the addition property. Right here, this is the addition property of equality. If I have an equation, quality. So if I have an equation that's true, I can add the same number to both sides and it's still true. That's essentially what that's saying. It's like if you have a scale or a balance, if you have a weight on it and you have it's balanced out, if you add the same, if a weight on the left side, you have to also add it on the right side for it to stay balanced. So that's what the equation is. The equal sign is all about meaning balanced. It means these things are the same. They weigh the same. They may be different numbers. They may have variables. They may have other things, but they basically weigh the same. They're treated the same. And so whatever I do on the left, in order to keep them the same, I have to also do it on the right. So that's where we get the subtraction property of equality. Basically, if I remove something from the left, in order for the scale to stay balanced, I have to also remove it from the right. And that rule comes from, well, I can add a negative to both sides of the equation. And then adding a negative is the same thing as subtraction, and that gives us the subtraction property of equality. So this subtraction property of equality here comes from the addition property of equality plus the definition of subtraction. So you see, we're using those same basic rules that we started with, and we're coming up with new rules. Now, the other properties of equality we have are multiplication and division. So normally, I don't write my multiplication that way. When I do it, I usually do it in the same line. But I wanted to make it clear that we're multiplying both sides. We start with something equal, we multiply both sides, and then we still have something equal. So multiplication is basically a repeated addition. So if I'm going to double what's on the left side of a scale, I need to double what's on the right for it to still be balanced. So it's all about balancing. And again, I can go through the rules with division, that dividing is multiplying by the reciprocal, and you can basically get to the rule that you can divide both sides by the same number. If I have something that's a scale, if I take half of the items left on the left, I need to remove half of them on the right. You need to, if you're gonna, you just have to do the same thing on both sides. So that's what these properties of equality are saying. So let's actually start doing some solving. Let's show you how these rules are being used and where they're coming into play to solve. So I'm going to start, and I'm going to also sort of kind of teach you how to take notes and just, when you're good practice for taking notes. So if you have a problem, you always write down the directions. So here, let's say I'm solving a plus 5 equals 13. So You always want to make sure you write down the directions, so that way when you're in your notes, you know what to do. So just as a side note here, the word solve means find what number makes the equation true. That's basically what this means. So you're trying to find out what number would we be allowed to put in for A. So we're looking at, we need to know what number works for A in order for this to be true. When you have simple equations like this, you can kind of do it mentally. Like I can look at this and I know 8 plus 5 is 13. But while that's fine enough for a problem like this, when you get in more complicated algebra, you can't do it in your head. So you want to learn the steps so that way when you get to the complicated stuff, you know what to do. So we are going to use our rules. If there was anything with subtraction, the first thing I would do would be rewriting it as adding a negative, because that's just good practice. My goal when I'm solving is to get the A, the variable, by itself. So I want to know what A is. So I need to get that by itself so I know A equals, and I know whatever it equals is the right thing. So I have this plus 5 on the left, and I don't want to have 5 there. I need to get rid of it. So the only way, if you have 5 things, you have to subtract them. You have to remove them. So I need to subtract 5 from both sides. So I'm going to start by, let's see, what's a good color here. So when I show my work and I take notes, I always start by rewriting the problem. So that way I'm not messing with the original problem, and I still know what the original problem was if I start messing with it. So I need to get rid of the 5. So I need to subtract 5. I need to remove it. And if I do it on the left side, I have to also do it on the right side, because then it's not balanced. So I'm going to write minus 5 on both sides. And it's always good practice to write down what you're doing. When you're taking notes, you don't want to just write down the equations, because then when you go back to your notes later, you'll be like, well, what was I doing here? So you need to make notes to yourself. So let's say, for example, I wanted to make a note here that my goal is A by itself. So that way I know what I'm trying to do here. That's my goal. So here, when I'm subtracting by 5 from both sides, I am using the subtraction property of equality. And so I'm writing that down. So that way, if you had to go back to your notes later and you're like, well, why did I do that? Why was I allowed to do that? You have your goal, so you know what you have here. And then you have what rule allowed you to do that. So I have, if I'm okay, I've got my A, because we always work vertically. Math always goes from top to bottom. 5 minus 5 is 0. And then 13 minus 5 is 8. So now I have A plus 0 equals 8. Adding 0 doesn't do anything. Basically, adding 0, it's once you have 0, it's meaningless, basically. So I can just ignore that and rewrite this as A equals 8. That rule that allows me to go from A plus 0 equals 8 to A equals 8, that is our identity property. So if you're wondering, well, why could we do that? It's because we have this rule about adding 0, that when you add 0, it doesn't do anything, and it's just the same as what you had. So that gives us our final answer here of A equals 8. So our goal was to get A by itself. We have A by itself, so that is our answer. Now, I like to box my answers. Some people will highlight them. So I wonder if a white highlight Oh, it doesn't like white highlights. Oh, it doesn't want to highlight at all. Oh, I guess it's highlighting a little bit, not really, because of the black background. But usually what I'll do is I'll just box the answer, just make it obvious that this is my final answer here. So we had a plus 5 equals 13, and then we're following our rules so that we can find out what that value of a is. And you can always put this in real life terms. You know, like if you don't like working with variables, you can say, okay, I have some number of apples and I'm having 5 more, and that gave me 13. So how many apples did I originally start with? I originally had 8 apples. So you can kind of put this in terms, make up a word problem so that it makes sense. Okay, so let's look at a different one. Let's say I have something 3x equals 18. So I want to solve 3x equals 18. So again, I'm trying to find an answer for x. What number can I plug in? And 3x is the same as 3 times x, if that makes it easier for you. So 3 times some number gives me 18. Mentally, I know that 3 times 6 is 18, but again, when we get a more complicated math, you can't do it in your head, so you need to learn the rules, even if it seems silly. So again, it's always good to start with your goal. So our goal here is we want x by itself. So we want to have x equals and then some number. You want to rewrite it that way. So I'm going to start by rewriting my problem. 3, and if it helps, you can put the multiplication sign in there between the 3 and the x. So normally, we don't write a multiplication symbol between 3 and x. It's called implied multiplication. We assume if a number is next to a variable, it's multiplication. But if it helps, you can write down that symbol there. You can put in the multiplication symbol so that it reminds you, okay, these things are multiplied together. So my goal is to get x by itself. And right now I have a 3 in front of it. And I don't want to have that 3 there. I need to get rid of it. So I can't make it 0 because we're multiplying here. My rule is if I have something that's multiplied, I have to do the opposite. I have to divide. So I can't subtract 3. I'm going to have to divide by something. So the best thing I can do is divide by 3 so that I get 1. So that is just 1 times x, and then I'm back to 1 times anything. Multiplying by 1 doesn't do anything. So what we're going to do is divide both sides by 3. So you always do the opposite of the sign. And I always write my division as a fraction because a lot of the time when you're solving, it doesn't come out to a whole number. It will often come out to a fraction. And so it's just easier to write your division as fractions because then you just know I need to reduce this if it doesn't come out. So here, what we are doing, we are using the division property of equality. Because I have 3 times something and I need to get rid of the 3. So to undo multiplication, you divide. So 3 divided by 3 is 1. So this gives us 1 times x on the left. And then 18 divided by 3 is 6. So I have 6 on the right. And 1 times x is the same thing as x times 1, and multiplying by 1 doesn't change your answer. So if I wanted to, I could rewrite this x times 1, and then that's just x. So we get an answer of x equals 6. So going from the 1 times x to the x times 1, rearranging that multiplication, that is our commutative property. Because looking at 1 times x, you might say, okay, I don't know what 1 times x is. X is some number, and I don't know what the number is. But if I look at x times 1, I know times 1 is, it doesn't change your answer. So that's easier to look at it in terms of x times 1, because you know multiply 1 doesn't change anything. So that's how you get x. So going from the x times 1 to the x, that comes from our identity rule again, our identity rule about multiplication. Because multiplying by 1 doesn't change things. So this tells us that our answer is 6. We got x by itself. So we've used our rules that we've learned to figure out what x is. Now, I've shown more steps here than I would normally, but it's a good way to see how these rules are coming into play. And I could even fill in some more steps here if I wanted to. I could, let's see, I could split up my multiplication here with the 3 times x divided by 3. I could rewrite it that way so that you can see that the 3 divided by 3 is equal to 1. I could get as deep as I wanted, right? You can write tons and tons and tons of steps here if you wanted. So these two problems are ones that you can do in your head. Now I'm going to show you why we learn these rules, because I'm going to give you a problem you can't do in your head. Or if you can do it in your head, then you probably are better at math than I am, because I will not be able to do this in my head. So let's say you were solving. Let's say we've got 2 times 1x. Actually, let's make that negative 1x plus 5 equals 10 minus 3x. So I have just made up this problem. This is not something that you can look at this and say, oh my goodness, I know what the number is that works here. Like, you look at it, you're like, I don't know, you know? This is the kind of problem that you guys are going to see, and you're going to be like, I don't know what to do. This seems too hard. I'm just going to give up. But if you go back to what you know and go step by step by step, you can go and solve this. So first thing that I always start is turning any subtraction into adding a negative. That's the first thing that I always do. So the left side doesn't have any subtraction, so that's going to stay the same. But on the right, we have minus 3x, so I can turn that into adding a negative 3x. Doing that makes things easier. And so this, we use the definition of subtraction here. That allows us to turn the subtraction to adding a negative. Okay, so now we look at this and you're still like, oh goodness, what do I do? Well, think about what you know. Order of operations. The order of operations, PEMDAS. So if we're going through the order of operations, parentheses, if there's things to do inside parentheses, you would. We have a negative 1x plus 5. Those are not the same thing, because one has a letter and one is a number. You can't add letters and numbers together. E stands for exponents. I don't have any exponents. So the next would be the M and the D, the multiplication and division. We have multiplication here. That's right here, we have our distributive property. We use the distributive property to multiply this out. So you're going through what you know. Okay, I turned my subtraction, adding a negative. Now I'm going through the order of operations. Order of operations says I should multiply. So let's do the multiplication here. So you're going to multiply 2 times the negative 1x. And I'm going to write down every single step here so that you can see we're multiplying 2 times the 1x for the distributive property. Then you're going to do 2 times 5. You always have a plus in between there. And then I didn't do anything on the right here. So what I just did here is the distributive property. So now let's take a look at what we have. We've got a 2 times 5, so that's multiplication, so I can do that. 2 times 5, that's 10. That's easy enough. So if I want, I'm going to just fill that in already. I know that's going to be 10. Now over here, we have 2 times negative 1x. And the negative 1, we have that implied multiplication there. Negative 1x. Negative 1 times x. So normally we don't write this step. We usually just multiply the numbers together, 2 times negative 1. But I'm going to show this step so you can see the rules here. The rule that we're going to use is the associative property. I can rearrange those parentheses. So I can do 2 times negative 1 and then have my x. So I can use the associative property there. So actually I should have put that right above because I already wrote that 10 in. 2 times negative 1, then x. And then I did 2 times 5, which is 10. We can do that. And then I didn't do anything on the right. But what I did in the orange, that is the associative property. We just use that so that I could rearrange and stick the numbers together. So I can do 2 times negative 1. So now I can actually multiply 2 times negative 1. I can do that math. So 2 times negative was negative 2. So I have negative 2 plus 10 equals 10 plus negative 3. So this is your thinking process. You're going through these problems. You're thinking. You're like, okay, what do I do next? Now I've got these things. Okay, I've got multiplication and division. What's next? Let's see. Order of operations, addition and subtraction. Let's use the addition and subtraction properties of equality. That, you know, if you think about what you know the order of operations. Let's do that. So we're going to do that. And whenever I use the addition property of equality, I like to have my x on the left when I'm solving. The x doesn't have to be on the left, but I like to put it on the left. So I have a negative 3x, and I want to put it on the left. I want to have all of my x's on the same side, and then all of the numbers on the other side. You want to have these things balanced here. So you do the opposite. If I have a negative, in order to get it to 0, to remove it from the right side, I need to add it. So I'm going to add 3x. And then whatever I do to the right, I have to do the left, and vice versa. So I'm trying to move my x's to the left, so I'm getting rid of that negative 3x by adding it. This is the addition property of equality that we're using. So I have a negative 2x plus 3x. You're adding the numbers. Negative 2 plus 3 is the same as 3 minus 2. And that comes from that subtraction thing that I did with the commutative property of subtraction. We saw that a negative plus a positive plus a number, that's the same as doing the opposite in subtraction. So 3 minus 2 is 1. So this is just 1x plus 10 equals 10. And then a negative 3x plus 3x is 0. And we know that 10 plus 0 is 10, so that's easy enough. So I have 1x plus, I should actually keep lining all these things up. X plus 10 equals 10. Now we're going to use the addition property of equality again, because I want to get the x by itself. Now I am back to the type of equation that we saw here. It's the same form as this type of equation. So I said everything goes back to things that we saw already. We have this big complicated thing we're figuring out using our what we know, and we found ourselves in a situation here where it's in the same sort of form. So I want to subtract 10 from both sides. I want to get the x by itself. I'm running out of room here. So I'm going to try to squeeze it in. But this is, again, we are using the addition property of equality. Or in this case, you can say it's the subtraction property because we subtract it. Because if I have positive 10, I have to remove 10 to get rid of it. So that gives us, we have a 1x equals 10 minus 10 is 0. Now 1 times x is the same thing as x. We saw that before, so I don't even really need that 1 there. Normally, if I had more room, I would write out every single step here so you guys can see all the rules we're using. But this tells us that our answer is 0. So if I put 0 in for x, I won't circle it there, that will make this equation true. And so we went through, we used what we knew. We said, okay, well, what do I know? Let's try this. What next? You go through your rules. You can see that sort of following the same order of operation rules. And then we got to a point where we couldn't do it anymore, and then we had to start moving things around. So hopefully this makes you understand what we're learning this week better, understanding those rules, why we have the rules, what they allow us to do, the thinking process behind solving. How do you know what to do, that sort of thing. So I'm hoping that this kind of helps you out so that way when you get to a problem, you can do the same kind of thinking to try to figure it out and go through the same sort of steps and solve it on your own.